So in chapter 9 we will study relations, and we start with the definition of relations and their properties. And we will start with binary relations. Binary here means relation between two elements. So a binary relation represents relationship between elements of two sets. So it's a relation of two elements. Each element is coming from a set. It could be the same set. So here there's the definition of relation. Let A and B be sets. Then a binary relation, this is how we say it, a binary relation from A to B is a subset of A cross B. Is a subset of A cross B. So the idea here is that we want to relate elements from A to elements from B. But that does not necessarily mean we want to relate every element of A with every element of B, or all elements of A. Every one of them must be related to some element of B. No, this is not what we mean. It might be in some cases, but not necessarily in general. But it says we relate some elements of A are related to some elements of B. An element of A and an element of B, then we will write them as ordered pair. The first coordinate contains an element of the set A, the second coordinate contains an element of the set B. And then we will say this element from A is related to this element from B. So how we do it, what is the relation now, is a subset of A cross B. You know, A cross B consists of all ordered pairs whose first coordinate is from A and whose second coordinate is from B. And we said we will relate some elements from A to some elements from B. That means we will take some subset of A cross B. Some subset of ordered pairs defines the relation. So this is what we are saying here. We will write A R B, which means A relates to B. And we will denote A, B as ordered pairs belongs to A. And here before that, maybe I will say a binary operation from A to B is a set R of ordered pairs. I shall complete the sentence, maybe it's better. Ordered pairs are coming from A cross B. And we will say that A is related to B if the ordered pair AB belongs to R. And then A is not related to R if the ordered pair is not in R. When the ordered pair AP belongs to R, we said A is related to B by R. Because we might define different relations. We say the relation is a subset of A cross B, so different subsets of ordered pairs define different relations. So some element A might be related to B according to some relation R, but these two elements might not be related according to some other relation. And we will see that. So simply, a relation is a subset of ordered pairs. A relation from A to B is a subset of ordered pairs whose first coordinate comes from A and second coordinate comes from B. Okay, and this example, a simple one, and make the idea clear. Choose A to be the set 0, 1, 2, and B to be the set A and B. Okay, now this is a relation here. This subset is a subset of A cross B. You know A cross B here has 6 elements, which means the order of A plus B has 6 elements. We are not taking them all here. We are taking 4 of them, and we define the relation according to these 4 ordered pairs. So this is the relation R. We might write R equals this set here. So 0 is related to A and 0 is related to B. This is possible. 0 related to two different elements. An element of A, this is A, this is B. An element of A might get related to two different elements in B. This is fine in the relation. Okay, and 1 is related to A and 2 is related to B. This is a good way to represent it. So 0 is related to A. We will just make an array or a row, and 0 is related to B. And 1 is related to A and 2 is related to B. And this is in here another way to represent the relation. 0 is related to A, so we put an X in here, mean that 0 and A meets together, they have a relation. 1 is related to A, 0 is related to B, 2 is related to B. Notice that we don't have anything in here because 1 is not related to B, so we will write the ordered pair 1B does not belong to R. And same thing here, the ordered pair 2 and A, 2 is not related to A, so this does not belong to R. So this is a good way to represent a relation, and we will use it. Okay. Now, functions as relations. A special case of relations is functions where we relate an element to its image simply. So here we go. You have seen this before. A is related to its image. Okay, so we will define a relation given f a function from A to B. So we will define a relation R to consist of all ordered pairs. So we will relate A to its image, where now A belongs to A, and for sure here f of A will belong to B. So we can define a relation upon a function. Okay, now what's happening here, recall that a function from a set A to a set B assigns exactly, so we have a function from a set A to set B, assigns exactly one element of B to each element of A. Okay, assigned exactly one element of B to each element of A. We have seen in the example above there that we have 0 related to two elements in here and in here. So the 0 is related to A and again is related to B. This is fine in relations. But when a relation is defined on a function, upon a function, this cannot happen, because the function takes an element and send it exactly, takes an element from the domain A and send it exactly to one element in B, exactly to one element. So this is what we are saying here. Assigns exactly one element of B to each element of A. And the graph of F is the set of ordered pairs. You know that. And now, because the graph of F is a subset of A cross B, then it is a relation. So what we are saying here simply, A and F of A is an element here. So that's in here in the last line. This is just explaining what I wrote in here as a relation. So we define a relation in this way. So every element in A is in the first the first element of exactly one ordered pair. Okay, is the first element of exactly one ordered pair. Okay, so a function gives a relation. Now, conversely, if R is a relation from A to B such that every element, so we have a relation from A to B such that, so remember, a relation is a subset of A cross B. So it is a set of ordered pairs. First coordinate is from B, first coordinate is from A, second coordinate is from B. But what we are saying here, if R is a relation from A to B such that every element in A is in the first element of exactly one ordered pair. So every element of A, you will find it as the first coordinate of exactly one ordered pair. We are assuming the relation is defined this way. Then that relation gives a function. Then a function can be defined with R as its graph, because R consists of ordered pairs, and you know ordered pairs are points, and then you connect them, you get a graph, right? So a function is defined with R as its graph. A function is defined upon a relation. What we have seen above there, starting with a function, then we can define a relation upon this function. Now we go in conversely. If we are giving a relation, can we define a function upon it? Now we are saying, if that relation, if every element, if every first coordinate in every ordered pair in that relation relates to one element only, if every element from A is the first element of exactly one ordered pair. This is what we are saying here. If every element in A is the first element of exactly one ordered pair of R, then we can define a function. Take that element to the second coordinate of the ordered pair. And this is the way. This can be done assigning to an element A a unique element B such that AB belongs to R. So we are saying every element in here in A appears exactly in one ordered pair. So we will take the second coordinate of that ordered pair to be the image of A. So this way, if we start with a relation, then we can define a function. So a function represents a relation where exactly one element of P is related to one element of A. So this is a repeating of what I said. Okay. So functions give relations, and some relation under some conditions gives functions. Okay. Relation on a set. So we are saying a relation from a set A to set B. It could be from a set A to A itself. Okay. So relation from a set A to itself are of a special interest. So a relation on a set A. At the beginning of the definition, we said a relation from the set A to the set B. Now A and B here are the same set, so we will say a relation on the set A is a relation from A to A. And that means it is a subset. In this case, this relation is simply a subset of A cross A, which means a subset of ordered pairs whose coordinate and second coordinate are each from the set A. And here is an example. If we take the set A to be 1, 2, 3, 4 and define R to consist of ordered pairs A and B such that the first coordinate defines the second coordinate out of this number. So we know that 1 divides 2, 1 divides 3, 1 divides 4. So we'll have 1, 2, 1, 3, 1, 4 to be in the relation. So this is the relation here. So 1, 1, 1, 2, 1, 3, 1, 4. We know that 2 divides 2 and 2 divides 4. Okay. And 3 divides 3 and 3 divides 4. So simply we will have, for example, 3, 4 does not belong to R because 3 does not divide 4. Okay? And this is a representation for this relation. 1 goes to 1, 1 goes to 2, 1 goes to 3, and 1 goes to 4, and so on. And this is also the matrix representation of the relation R. And you can check it. Okay. Another relation on a set, from set to itself. So here, the set of integers. So we are using the set A to be the set of integers. And we are defining 6 relations now on the integers. First relation says that we will define A to be related to A to be related to B if A is less than or equal B. For example, 1, 2 belongs to R1. 1 7 belongs to R1. 1 0 does not belong to R1 because 1 is not less than or equal 0. Okay. R2 says A is related to B if A is greater than B. R3 says A is related to B if A equals B or A equals negative B, which means two integers are related if they have the same absolute value. Okay, so let me go here and say, let me go back to R2. Let me give an example for R2. So we will have 7 and 6 to belong to R2, but 7 and 7 does not belong to R2 because 7 is not greater than 7. Okay, and also we will have negative 3 and negative 1 belongs to R2. No, does not belong to R2 because negative 3 is less than negative 1. But we will have that negative 1 and the negative 5, for example, belongs to R2 because negative 1 is greater than negative 5. Okay, R3. So we will have any integer. We can define R3 to be the following. R3 can be defined to be the set A, negative A, where A is an integer. So A can be positive or negative. When A is positive, the first coordinate, then the second coordinate is negative. Or, okay, no, I'm missing something here if you notice. I need to add, because R3 will relate elements to itself, right? So I will say the following. Okay. I will say it consists of A, comma, A negative A, where A is an integer of Z. So every element is related to itself and is related to its negative image. Otherwise, ordered pairs will not be in this relation R3. Now R4 is very direct. A and B are related to each other if they are equal. So simply we will say 3 negative 3 does not belong to R4, while 3 and negative 3 belongs to R3. Okay, R5 says that two integers are related if the first integer is 1 greater than the second integer, if A equals B plus 1. And for instance, we will say 6 and 5 belongs to R5. And also we will say negative 7 and negative 6 belongs to R5 because negative 7 is negative 6 plus 1. Okay, R6, it says that two integers are related if their addition is less than or equal to 3. If their addition is less than or equal to 3. Okay, so we will have, for instance, negative 4 and 7 to belongs to R6 because negative 4 plus 7 is 3. Okay, and also we notice that if we reverse the order of these two elements, we will still have this in R6 because changing the coordinates, the places of the coordinates, will change the addition of the elements. But we know changing the places of the addition will not change the result. Okay, now go again here. We have some ordered pairs. Where one belongs to. List all the relations above there where the ordered pair 1 1 belongs to the relation. So I need to go back to fix this one. I must say here minus 6 minus 7 belongs to R5. Okay, but minus 7 minus 6 does not belong to R5. We got an ordered pair in R5 which belongs to R5, but if we change place of coordinates, we get a new ordered pair which does not belong to R5, and we will need that thing to say to define some relation that are symmetric or not symmetric. We will see it later. So are we doing fine so far? So okay, so we have one problem here and we fixed it, and this is fine. Okay, now what about the ordered pair 1 and 1, where 1 and 1 belongs to? Does it belong to R1? So 1 and 1 belongs to R1, correct? Does it belong to R2? No. It belongs also to R3. Does it belong to R4? Yes, belongs to R4. Does not belong to R5, and it belongs to R6. So 1 and 1 belongs to all of these. Okay, what's about 1 and 2? And for sure 1 and 1 does not belong to any other relation. What about 1 and 2? Does it belong to R1? Yes. Does it belong to R2? Is 1 is greater than 2? No. Does it belong to R3? No. To R4? No. And to R5 does not belong because 1 is not 2 plus 1. And to R6, it belongs to R6. So do you agree with that? Okay. R1, R4, R3, and R6. So yeah, this is 1 belongs to R6 also, because 1 plus 1 is less than or equals 3. What's left? Let's go to 2 and 1. Does it belong to R1? No, because 2 is not less than or equal 1. Does it belong to R2? Yes, because 2 is greater than 1. Does not belong to R3 or R4. It does belong to R5. And it does belong to R6, because 1 plus 2 is less than or equal to 3. Okay, now what else? 1 and negative 1, so we need more space. Let's move this. What's about 1 and negative 1? It belongs to R1? No, does not belong to R1 because 1 is less than negative 1. But it belongs to R2 because 1 is greater than negative 1. It belongs to R3, correct? It does not belong to R4 and does not belong to R6 because 1 does not equal negative 1 plus 1. And it belongs to R5, sorry. Now it belongs to R6. Okay. Now if I did any mistake, please remind me. Okay, so yeah, so we agree with the answer. Now 2 and 2. It belongs to R1. Does not belong to R2, but it belongs to R3 and R4. Does not belong to R5, and it does not belong to R6. Okay, so we agree again. Thank you. So good. Those are we are doing fun here, so we're having fun. Now a question here: how many relations we can define on a set with n elements? Okay, so can you answer that question? So a relation on A is a subset of A cross A. But the number, we need to think the number of subsets. So you gave me an answer and I said correct, but it is not very correct. Think about it again. But the number of subsets of A cross A is equal to what? To cardinality of the power set of A cross A, correct? Because this is the number of subset, is the number of elements of power set. But this cardinality is 2 to power, somebody said n squared there, A. So 2 to powers, and the power will be the cardinality of the set that we are taking the power set for. And that means 2 to n squared, because we know that the cardinality of A cross A is n times n, which is n squared. So the number of many subsets we are asking on a set A is 2 to n squared. Okay, so the beginning we said 2 to power n. Okay, and Aruba says n squared, 2 to power n squared. Good, thank you. Okay, good. So now we will study some properties of relations. A relation A on a set A, so we are taking a relation from A to itself, is called reflexive if every element is related to itself, which means the ordered pair AA belongs to R for every element in A. That means if we write it in quantifiers, for every A, the ordered pairs AA is in R. Then we will say reflexive. Every element is related to itself. Every element is related to itself. Then we will say reflexive. Now we have here relations on the set AB and the set A, which consists of the integers 1, 2, 3, 4. So this is A. Now here we are defining different relations. R1. Is R1 reflexive? So we must A contains 1, 2, 3, 4. So for a relation on A to be reflexive, we must have 1 related to itself, 2 related to itself, 3 related to itself, and 4 related to itself. So we must have 1, 1, 2, 2, 3, 3, 4, 4 to exist in that relation. To exist in that relation, so that we say it is reflexive. So what do you think about R1? So we have 1, 1 here, we have 2, 2 here, we have 4, 4. But we don't have 3, 3. So R1 is not reflexive. Since 3, 3 does not belong to R1. So I will say not reflexive on as must specify on A, because I want every element of A to be related to itself. If A is 1, 2, 4, then this R1 will be reflexive if the 3 is missing from the set A. Okay. And so which one is reflexive? So here R2 we have 1, 1. So we are missing 2, 2, 3, 3, 4, 4. So this is not reflexive. R3 we have 1, 1. We have 2, 2. We have 3, 3, 3. We have 4, 4. So this is reflexive on A. And I will say here always on A. What's about R4? We don't have no 1, 1, 2, 2, 3, 3, 4. So this is not reflexive on A. In R5 we have 1, 1, 2, 2, 3, 3, 4, 4. This is reflexive on A. R6 not reflexive on A. Okay, so this is simple. Remember that the ordered pair of AE for every element A. The first relation misses or missed 3 3, so it is not reflexive. Now, okay, which of these relations are reflexive? And our set here again is the set of integers. Okay, now in R1, is every integer related to itself? In R1, is every integer is less than or equal itself? Let me pause that. This is reflexive, true. And okay, Amjad, R1, R3, R4, R1, R3, R4, R1, R3. So all of you agree at R1, R3, and R4. And R4, yes. Every element is related to itself. Every integer is related to itself according to these relations. And this is not reflexive, not reflexive, not reflexive. Okay, good. Now what's about this example here? Is the divides relation in the set of positive integer is reflexive? Give me the answer, please. Is it reflexive? Which means we're defining here R to be consists A B such that A divides B. Is that reflexive? And this is yes, reflexive. Reflexive since every element divides itself, and this is true for all integers in Z. So this relation is reflexive. Okay. In R3, every element is related to itself. It contains, like we mean here, A belongs to R3 for every A belongs to Z. This is correct, right? So every element is related to itself, so it is reflexive indeed. Right? And the set here, the positive integer. So I will say the set of positive integer. We avoided the 0 here. The 0 is not contained. So I will say Z plus means the set of positive integers. So this relation will be reflexive in the set of positive integers, avoiding the 0. So it says an or, which means we have or means we have this or that, or we have both of them. So we have A, and I just wrote that operation before that relation. It consists of A and A negative A, where A belongs to Z. So we will have or here is not the exclusive or, it is the inclusive or. So we'll have this or this. Or here means, so going back again to or here, A is related to B if A equals B, or A equal negative B. In either case, A will be related to B. Okay? So A will be related to itself because it equals itself. So R3 will be reflexive. Okay. And now I hope this gives an idea of these relations in here. So we have seen some of the elements of R. Okay? So 1 divides 1, 2 divides 2, 3 divides 3, 4 divides 4, 5 divides 5, 6 divides 6. Every integer divides itself. Every positive integer divides itself. So A divides A, where A is an integer, belongs to R. So I hope this is 0. Why we did not close 0? Because our set here that we are defining the relation on does not contain 0. So we started set this way. Now if we allow the 0, make a new set where 0 is there, then we cannot define this relation because 0 does not divide 0. Or we will say, I mean, we can define that relation, but 0 will not be related to itself. So this will be a good example. So let's go for it. Let me go to this side and then make another example. Now we know the natural numbers contains the 0, right? We agree in that. So they are non-negative integers. Okay. Now define R the same as in the first example, the divisibility, but I will write it this way: AB. So define R on the natural numbers such that A divides B. Then R is not reflexive, and you already said the reason, since 0, 0 does not belong to R. Now it is not reflexive. So defining a relation, the same rule, the same method of relation on different sets produces different properties. Good? Okay. Okay. Now, what we have seen in the example above, in some relations, an element is related to a second element if and only if. So this is something happening. An element is related to the second element if and only if the second element is related to the first element. Which means if A is related to B, if A, comma B belongs to R. So we are saying here AB belongs to R. This is the first element related to the second element. And we are saying here if and only if, this is if and only if B belongs to R. This is the second element now. This is first element in the beginning. Okay. So AB belongs to R if and only if B belongs to R. So it is an element is related to a second element if the second element is related to the first element. So we are changing the position of elements. A is related to B, then B is related to A. Now, we are saying here some relation forces this. If A is related to B, then that relation will tell you, okay, so B is related to A. If you get A related to B, then I am as the relation will force you to do the opposite and say B is also related to A. This kind of relations is called symmetric. So when a relation do such a thing, when a relation have such a property, then we will call it symmetric. So here we go. A relation on a set A is called symmetric if B will be related to A whenever A is related to B for all AB. So if whenever we are not saying for every element in A, two elements in A, they must be related to each other in opposite ways. No, we are not saying that. We are saying that if we find an element related to B, then we must have also that B related to A, changing the places. Okay? So B will be related to A whenever A was related to B. And then we call it symmetric. Now, if it happens that there is some element, okay, that relates to B, and also B related to A, this does not happen unless A equals B. See, this is what I'm saying. If R is a set on A such that if A is related to B, and B is related to A, then we must have that A and B equal. And in such a case, it is called antisymmetric. Antisymmetric. Do you still see me? Because my picture disappeared and then came back again. Okay, thank you. Now, let's understand this. We have got the idea of symmetric. If A is related to B, A comma B is in R, then B comma A must be also in R. We agree? Okay. Now, what's about the antisymmetric? Let's read the sentences below here. Let's go back to the symmetric. A relation R is symmetric if, using quantifiers, for every A and every B, see what that means? For every A and every B, what happens? If AB belongs to R, then BA belongs to R. This is easy. Or also, we will say it is symmetric if and only if A is related to B implies that B is related to A. This is what I said already. Now, what's about the antisymmetric? The antisymmetric does not allow this to happen. The antisymmetric does not allow two elements to relate to each other in opposite ways unless these two elements are the same element. Does not allow different elements to relate to each other. So, antisymmetric relation does not allow distinct elements to relate to each other in both directions, in both ways. Okay? And this is now is written here. Now, again, the antisymmetric, R is antisymmetric if, whenever, for every A and every B, what happened? If we have A and B related to R, in R, A and B, A related to B, and B related to R, then we must have that A and B are the same. If A related to B and B related to R, we cannot allow A and B to be distinct. We cannot allow them. This is what R says when it is symmetric. If A related to B and B related to A, then A and B are the same element. The relation R is called antisymmetric if it does not allow, here we go. It's called antisymmetric if and only if there are no pairs of distinct element. No pairs of distinct element, A and B, with A related to B and B related to A. There are no pairs of distinct element, A and B, that are related to each other in opposite ways. Okay? So this is called antisymmetric. And this is also to explain what antisymmetric is. It says the only way to have A related to B and B related to A is to have A and B to be the same element. So I think now this is enough explanation of antisymmetric. Okay. Now, for instance, an example of antisymmetric. The less than or equal relation is antisymmetric because if A is less than or equal B, this is A related to B, and B is less than or equal A, this is B related to A, then A and B are the same element. So this is an antisymmetric relation. Okay. Now, a relation cannot be both symmetric and antisymmetric if, be careful, a relation can be both symmetric and antisymmetric, but there is some case that does not allow this to happen. So, if it contains some pair of the form AB in which A does not equal B. So, it says a relation cannot be both symmetric and antisymmetric if it contains an ordered pair of this form with A does not equal B. Okay? Now, why is that true? If A is symmetric, okay, so let's stay here. If A is symmetric, if R is symmetric and AB belongs to R, then we must, AB belongs to R, then we must have BA belongs to R, because we are saying it is symmetric. And we are assuming here A is not equal to B. So this goes against the antisymmetric, because antisymmetric does not allow this to happen. So this relation now is symmetric, but it is not antisymmetric. Now, I will say if A equals B, that means R is not anti-symmetric. So if A is related to B, A is not B, does not equal B, and R is symmetric, then B is related to A. So A related to B and B related to A and B are not equal, then for sure it is not antisymmetric. Okay? So good. So it cannot be symmetric and antisymmetric at the same time. So question 10 asks us to give an example. We will see more examples of this. Give an example of a relation on a set that is both symmetric and antisymmetric. So there are some relations that can be symmetric and antisymmetric. But we have seen above there one case where this cannot happen. So I will give you a chance to answer this question. Think about it. I will pause recording. So these are two examples of symmetric and antisymmetric. Both of them are symmetric, correctly. Antisymmetric, okay? No element is related to the other, and the opposite, the other is related to the first, unless they are the same element. So, okay. Now tell me about B. Give me a relation in which neither symmetric nor antisymmetric. A relation which is symmetric but not asymmetric. Okay. Now, two different elements, 3 and 4, are related to each other in different orders, but they are not equal. They are distinct elements that are related to each other in different orders, and they are distinct. So it is not antisymmetric. And it is not symmetric because, as we said here, 1, 2 belongs to R, but 2, 1 does not belong to R. So great, Sumaya, thank you. So this is a good example. Amjad Al-Wardi, AB, BA, CD. This is in general, yes, Amjad. This is in general another example of anti-symmetric. Good. Okay. Now let's go to the example here. Consider the relations on 1, 2, 3, 4, the ones we have already seen. Now, which one is anti-symmetric and which one is symmetric? So let's go for it. So I will give you a chance to answer that. So you have all the relations from R1 to R6. Classify them to be symmetric or not symmetric. What about R1? Is it symmetric? So give me the answer. R1. Okay, so let's start with them. R1 is not symmetric, right? Because we have 3, 4 in here, but we don't have 4, 3. Correct? And is it anti-symmetric? Not anti-symmetric, right? Because we have 1 related to 2 and 2 related to 1 and 1 and 2 on different elements. Okay, what's about R2? Tell me. Is it symmetric? Yes, it is symmetric. We have 1, 1 related to itself, 1, 2 and then 2, 1. Good. Is it anti-symmetric? Okay, no, it is not good, not anti. Symmetric. What about R3? So we have 1, 2 here, 2, 1 here, 1, 4, 4, 1, and so it is symmetric. Ibtisam, good. Is it antisymmetric? We have 1, 2, and 2, 1, and then it is not anti-symmetric because we have 1, 2 related, 1 related to 2, 2 related to 1, they are not equal. What's about R4? Is it symmetric? Notice we have 3, 1, but we don't have 1, 3. So this is not, okay, Sumaya, not symmetric. Is it anti-symmetric? Now answer me, is it anti-symmetric? Yes? Antisymmetric says if we have A related to B and B related to A, then A and B are equal. Now we have no ordered pair where the first element related to the second element and then the second element is related to the first element. There is no such ordered pairs. Okay? So nothing go against the anti-symmetric. What about R5? Is it symmetric? Now we have, it is not symmetric. We have 1, 2 here, but we don't have 2, 1. So this is not symmetric. What's about anti-symmetric? It is not anti-symmetric? Are you sure? What? Not anti-symmetric? What's happening? There is an element okay, it is anti-symmetric or not? Answer me. I'm still looking. It will be not anti-symmetric if I have A related to B and B related to A, but they are not equal. Do I have such a thing? I don't. So it is an anti-symmetric indeed, because I don't have A, B, and B, A for different distinct elements A and B. I don't have such a thing, so it is anti-symmetric. What's about R6? Is it symmetric? R6. Not symmetric. I have 3, 4 in there, but I don't have 4, 3. It is anti-symmetric. Yes, it is anti-symmetric. Thank you. This is great. Thank you very much. Good. Now let's go to the relations on the integers and let's have fun with them. Which ones are symmetric? Which ones are not symmetric? Let's go to R1. Is it symmetric? R1. Which one is symmetric? And classify them, symmetric or anti-symmetric. R1, is it symmetric? Symmetric. Is it anti-symmetric? So R1 is symmetric. If AB is related, no. I'm saying yes. No, I'm saying something wrong. It is not symmetric because we will have for example 1, 2 belongs to R1, but 2, 1 does not belong to R1, so it's not symmetric. Is it anti-symmetric? We just have seen it, huh? So it is anti-symmetric. This one is anti-symmetric. We just seen it above there. If A is less than or equal B, and B is less than or equal A, that necessarily means A and B are the same element. So it is anti-symmetric. It is, right? Okay. What's about R2? R2 is not symmetric. Yes. are two not symmetric. You can see that easily. Is it antisymmetric? And it is antisymmetric, yes. No, it is not antisymmetric. It is antisymmetric. We will not have A related to B and B related to A because there are no integers, two integers, A less than B and B less than A. There are not such a thing. Okay? So it is antisymmetric. We have seen in the relations above there some ordered pairs, some relation that contains ordered pairs, but it does not contain the opposite order pair of any of them. So it was antisymmetric. So, okay. R3 is what? Is it symmetric? Yes. Is it antisymmetric? R3, is it antisymmetric? If A is related to B and B is related to A, okay, what do you think? No? Some people saying no. It is not antisymmetric. Give me an example. The ones who said it is not antisymmetric, you must give me an example. Since, give me numbers. Thank you. Thank you, Sumaya. Because negative 1, 1 and 1, negative 1 belongs to what? This is R3. But negative 1 does not equal 1. Okay, so it is not antisymmetric. Let's continue. Tell me what's about R4. Is it symmetric? And antisymmetric, right? This is symmetric. And, okay, you agree. Antisymmetric. What's about R5? R5, tell me. Is it symmetric? Amjad, okay. So it is not symmetric. Right? And it is antisymmetric. هنا بتصير هذه الحالة. In this case, we don't have AB and BA. We don't have at all AB and BA in R5. Okay? What about R6? Is it symmetric? R6. R6, is it symmetric? It is not symmetric? No? No? Amjad, yes. You are right. Amjad, tell them yes, why it is symmetric. If A plus B less than 3, then what we get? B plus A less than 3 or equal 3. That means AB belongs to R6. This is A. And that means BA belongs to R6. So we get that. So this is symmetric. Is it antisymmetric? No, it is not antisymmetric. 1, 2, 2, 1 belongs to R6. So it is not antisymmetric. Okay, great. Good. What's about the divides the relation on the positive integer? Is this symmetric or is it antisymmetric? On the positive integer, again, we have no 0 in here. If A divides B and then B divides A, then if A divides B, if A divides B, then B divides A. So you are saying this is not symmetric. Give me an example. We will say 3 divides 6, but 6 does not divide 3. That means 3, 6 belongs to R. But 6, 3 does not belong to R. Is it antisymmetric? If A divides B and B divides A, then we must have A equals B. Is it antisymmetric? I mean, if AB belongs to R and BA belongs to R, that means A divides B and B divides A. Then what we get? Agree? Yes, so it is antisymmetric. Why you did say, well, okay, why you did not tell me that A might equal to negative B? Then A and like A divides B, negative B, and negative B divides A. This is possible. Okay, because we are working a positive integer. So if we say if we cancel this, if we say on the integer themselves, then it will not be antisymmetric. Okay. Let me say if this relation is on Z, then it is not antisymmetric. And give me an example. While to say that a relation is not symmetric or not antisymmetric, one example is enough. Is not anti-symmetric, since, give me an example, 3 divides negative 3 and negative 3 divides 3, but they are not equal. So that means 3 negative 3 belongs to R and negative 3 belongs to R, but they are not equal. Okay. Okay, good. A relation is called transitive. So we are defining a relation of a set on a set A. So from A to A. It will be called transitive. متعدية. If A is related to B and B is related to C, then A must be related to C. So A related to B and B related to C, then we must have a transition A related to C for every A, B, and C. And using quantifiers, we have that. For every A, B, C, if this happens, A related to B, AB belongs to R, and BC belongs to R, then we must have that AC belongs to R. So using quantifiers. Now let's have fun. Which of these relations is transitive? Okay, now let's start telling me. R1, is it transitive or no? 1 is related to 2, I can see. 2 is related to 1, and 1 is related to 1. Good. What else? 3 is related to 4. 4, see here? 3 is related to 4. 4 is related to 1. So 3 related to 1? No. So this is not transitive. So I will keep writing just no or yes. What's about R2? 1 is related to 2, 2 is related to 1, and then 1 is related to 1. So is it transitive? Yes. Good. Okay. What about R3? Is it transitive? 1 is related to 2, 2 is related to 1, so I get 1, 1, 1 to 4, 4 to 1, then 1, 1, 2 to 2. Okay, what do you think? R3, is it transitive? No? Why not? Let's see. 1 is related to 2, and 2 is related to 1, so 1 is related to 1. We have it here. 3 to 3. Where? Now 1 is related to 4, 4 is related to 1, and then 1 is related to 1. 2 to 2, 3 to 3, 4 to 4. What's the problem? What's the problem with 3, 3? So is it transitive or no? Aruba, Sulaiman saying yes, and it is yes. We have no problem with 3, 3, Mawadda. Okay. What about R4? Is it transitive? So do we have first coordinate to second and then second going somewhere? 2 to 1. Okay, we have no 1 to go. 3 to 1. We have 3 to 2. Okay, we have 3 to 2 and 2 to 1. So we must have 3 to 1 if we want to be transitive. But if 3 to 1 is not there, so this is not transitive. Okay, so 3 goes to 2, 2 goes to 1, so we must have 3 going to 2. But we don't have 3 going to 1. We don't have that. It does not belong to 4. Okay, what's about 3, 1? It's not there, you mean? It is there? It is not there. In R4, 3, 1. Okay, it is there. Oh, sorry. It is there. Okay. Okay, so let me erase that. Now, so let's keep going. Now, 3 going to 1. Okay, 4 going to 1. And then, okay, 4 goes to 2. And then 2. Okay, we have 4 goes to 2. So let me take this now. 4 goes to 2. And 2 goes to 1. And we have 4 goes to 1 here. Good. 4 goes to 3. 3 goes to 1. 4 goes to 1. And 4 goes to 3. 3 goes to 2. 4 goes... Okay, I can see it is transitive. Okay, I checked out. So it is yes. Check it out. It's transitive. What's about R5? What's about R5? So we have 1 go to 2. 1 go to 2. And 2 goes to 3. So we must have 1, 3. 1 if 3 is there. So okay. 1 have 1, 4. 1, 4 is there. 1 goes to 3. 3 goes to 4. 1, 4 is there. So I can see R5, is it transitive? So we are computing how 2 goes to 3. 2 goes to 2. 2 goes to 3. 2, 3. Okay. Is it transitive? Yes. What's about this? 2 goes to 2. 2 goes to 3. Do we see 2, 3 in there? I don't see 2 and 3 in there. 2, 3 does not belong to R5. Wow. So I need I need to open my eyes a little better. 2, 3 is there. Okay. So you think it is transitive? 2, 4. Can I see 2, 4 is there? Okay, so it looks to me transitive. 3, 4, and then 4 goes to 4. Okay. So it looks to me 2, 3, 3, 4, and then goes to 4. We have 2 goes to 4. So it looks to me, yes. It looks to me it is transitive. Are we missing something? Two, 4 is there. Here it is. So I believe it is transitive. I checked them all. I think it is transitive. What's about R6? It consists of one order pair. What about R6? Is it transitive? R6, no, it is not transitive. Transitive says if A related to B and B related to C, then A related to C. Now I have A related to B. I don't have anything else here. No, again, it's not transitive. Sumayya, what do you think, guys? This is transitive or not? I believe it is yes. Fix me, please. Correct me. Well, it says if A related to B and B related to C, then something happened. But we don't have this, the hypothesis, we don't have it. Okay? Now, 3 is related to 4. Now we want 4 to relate to something, and then we say 3 to relate to something, okay? But it is not happening. Okay? So again هنا بالعربي المتهم بريء ما لم تثبت إدانته. يعني هي transitive unless you show it is not. Can you show it is not transitive? Because there is no B and C which forces this to happen or not. So the definition of the transitivity is not violated. Is it violated? If it is not violated, then we are done. You agree? Because we will finish in 5 minutes. Okay, what's about these relations now? Tell me for a quick, please. Are they transitive or not? R1, is it transitive or not? So yes, this is transitive. R2, A is greater than B, B is greater than C, then A is greater than C, it is transitive. R3 must be yes. R4, yes. What's about R5? R5, tell me. R5, is it transitive? No? Why? Give me example. Give me example. We will say 6 and 5 belongs to R. And what? 5 and 4 belongs to R, correct? But 6 and 4 does not belong to R. This is for R5. So this is not transitive. What about R6? R6 is not transitive? Give me an example. I will let you think about it. Huh? Is not transitive? Give me an example. Is not transitive. Shall we work an example? 1, 2 belongs to R, and then what? Is not? It looks to me yes. No. Let me say 2, 2 belongs to R, and 2. Okay. It is. It looks to me. It is. 2, 2 belongs to R. No. Sorry. 2, 2 does not belong to R. 1, 2 belongs to R, and then 2 and. Okay. So if A, B less than or equal to 3, let me see that, and B plus C less than or equal to 3, does that give? This is the question. A plus C to be less than or equal to 3. I am suspecting that because I will choose. Okay, maybe. So I don't need this now. So think about it. We want to transitive 1, 2, and then 2 something. A, B, and then B, C. So 1, 2, 2, 0, 1, 0. So that does not conflict the transitive. 1, 0 belongs to the relation, right? Because 1 plus 0 is less than 3. So A plus okay. A plus B is less than 3, and B plus C is less than 3. So what we will have here, A plus C to be less than 3. My mind is hurrying, so I must slow down to think about it. Okay. Now my mind is going. So it is not a transitive because we have 3 0 and 0 3 belongs to R, but 3 3 does not belong to R. So somebody gave the same example I got, Sumaya. Okay, great. And now 2 1 1 2 and 2 2 again. Yes, this is another example. 2 1 1 2 belongs to R, but 2 2 does not belong to R. So when we think about in hurrying, then we cannot think. So let's slow down. Okay, is the device relation the set of positive integer transitive? Huh? Is it transitive? Show me your answer. Transitive or not? Positive integer, the set of positive integers, no zero in there. So if A divides B and B divides C, can we conclude that A divides C? That means AB belongs to R, BC belongs to R, and that gives for sure AC belongs to R. So it is transitive. So the answer is yes. Okay, so you agree with me in that answer. Okay, now combining relations. Relations are subset of A cross B, right? Subsets. So when we take a relation which is subset of A cross B and another relation R1 and R2 which is another subset, can we make union and then we get a new subset? This new subset is a new relation coming out of the union of R1 and R2. So in the same way two sets are combined, we can combine relations. For example, if A is this set and B this set, and R is defined on A cross B, R1, each of R1 or R2 are subset of A cross B. So relation is each of R1 and R2 is a relation from A to B. So notice this. When we make a union, we get a new set of ordered pairs. So we got a new relation. Good. So we got a new relation. So A is related to B, and under this relation, if I call it R3, so A is R3B if A is R1B or A if is R2B. What I said here, A is R3B, which means A is related if A is related to B through the relation R1 or A is related to B through the relation R2. Okay, what is the intersection? Just go and there are sets, intersect them. Then the only element that is we have only one element related to itself under R1 and R2. Okay, R1 minus R2, just go do operations of sets, R2 minus R1, just operation of sets. So we are doing nothing, and each time we get a new set of A cross B, and this new set is the relations, the new relations coming out of R1 and R2. Okay, now let us see other examples of that. Let R1 be x related to y of x if x is less than y, and R2 if x is greater than y. Then their union, then x is related to b according to their union if x is less than y or x is greater than y, but they are not equal. So you can see it here. Now what about the exclusive relation? And we know that means A circle plus B equals, we will have A union B minus A intersect B. So we will have the sets that are in A but not in B, and the sets that are in B not in A. So what we get, the sets, their union minus the intersection. So their union is this in here. So what is the intersection of these relations? The intersection of these relations, x less than y, x is greater than y. So what is the intersection of this relation? Is it phi or what? It's phi, right? I want an element, two elements where x and y, where x is less than y and y is less than x. We cannot have this. Okay. Now we combine the relation also using composition of functions. So the first method of combining relations is using the set operations: union, intersection, subtraction. And now we can combine composite relations. R compose S compose R. How we do this? R from a relation R is from A to B. Okay. A relation S is from B to C. Okay. So we have A going to B, going to C, and this is R, and this is S. Now we can compose R, we apply R, then we apply S. Okay, so jumping from here to here, so that need more space above there. Jumping from here to here is applying R first and then applying S. So S compose R. And here we go, the definition of it. Here we go. If A, B belongs to R, and then B, C belongs to S, then A, C belongs to R compose S. Here we go. So this belongs to, S compose R. Okay? So if I want to make it clear here, I'll rewrite it a more organized way. A, B belongs to R. BC belongs to us, and then this will gives me, so this is from B to B, so A is related to B, B is related to C, then A is related to C. Under the composition, first we got R, and then we applied R, then we applied S. Okay. An example of composition of functions, composition of relations. Okay, so in here we will see what is the composition of R and S, where R is the relation from 1, 2, 3 to 1, 2, 3, 4, and it is given this way. And S is a relation from 1, 2, 3, 4 to 0, 1, 2, and it is given that way. And the composition will be the following way. Now, how did we compute? How did we know the composition is the following? The easiest way to do it is to follow such a diagram. Now let's go to R1. R1 sends 1 to 1, so this is R1, R I mean. So it sends 1 to 1, and also it sends 1 to 4. So we will make a rows 1 to 1, 1 to 4. Okay. Also it sends 2 to 3. Here we go, 2 to 3, and then 3 to 1, and then 3 to 1, and then it sends 3 to 4. So we got R. Now for S, it sends 1 to 0. So we listed here, we listed the elements where R starts from. And in here, we listed the elements where R ends. Okay? And it should be the same set where S starts from. Okay? So this is 1, 2, 3, 4. 1, 2, 3, 4 is the set where are landing in, ending to, and it is the same where S is taking off, starting from. And then now we represent the element of S. S goes to 0, 1, 2, so we have in here 0, 1, 2, and let's see, 1 goes to 0, and 2 goes to 0, here we go, 1 goes to 0, 2 goes to 0, 3 goes to 1, 3 goes to 2, here we go, 3 goes to 1, and 3 goes to 2, and 4 goes to 1. Okay, good. Now, how we compute the composition? We just follow the paths. So, this is a path going from 1 here, here. So, this is a path going from here to here. So, we will have 1, 0. Here we go. This is 1, 0. This is one path. Another path going from 1 to 4. Here we go. 1 to 4. And then 4 to 1. Which means we are going from 1 to 1. Here we go. Okay. Another path. 2. 2 goes to 3. Here we go. 2 goes to 3. And 3 goes to 1. So 2 goes to 1. And also 3 goes to 2. So we have two paths. 2 going to 3 and then to 1. 2 going to 3 and then to 2. And then we have that. Again. 3 goes to 4. And 4 goes to 1. So 3 goes to 1. Here we go. One more. 3 goes to 1. Here we go. 3 goes to 1. And 1 goes to 0. So we get 3 goes to 0. So the best way to do composition of relations is to present them with arrows. It is much easier. Or if you want to go here, 1 goes to 1. This is in R. And then you go to S and see where 1 starts, at which ordered pair has 1 at the first element. It is here, and 1 goes to 0. So I have 1 goes to 1, 1 goes to 0, then I get 1 goes to 0. But it is easier to do it using the arrows. Okay, so one last thing here is to do composition of a relation on a set. To do composition on a relation on a set itself. And this composition as many times as we want. So it is R to power n. So R to power 1 is R itself. Here we go. This is, for example, R. Let's do R square. Let's do R square. And we will follow the way of arrows. So this is R starts from 1, 2. So A here is 1, 2, 3, and 4. So 1, 2, 3, 4. A goes from 1, 2, 3, 4 to 1, 2, 3, 4. Now, according to the relation, 1 goes to 1. Here we go. 1 goes to 1. 2 goes to 1. And 3 goes to 2. And 4 goes to 3. Okay? Now, if you want to compute R square, that means I want to represent the relation again. So this is R. Now I want to present R again. So 1 goes to 1, 2 goes to 1, 3 goes to 2, and 4 goes to 3. Now to compute R square, we will follow the paths. So here is a path. 1 goes to 1, and then this one goes to 1. So R square will send, so R square will just start from A to A itself. So it sends 1 to 1. Okay. And now again, 1 goes to 2 and 2 goes to 1. So we got 2 goes to 1. One more. 2 goes to 2 and 2 goes to 1. So we get 3 goes to 1. One more. 3 goes to 4 goes to 3 and 3 goes to 2. So we get 4 goes to 2. To compute r to power 3, so we have to compose r square and r. So let me here write r. R takes 1 to 1, 2 to 1, 3 to 2, and 4 to 3. So let's compose these two things. So this is r, and that's r square. Now we will get r to power 3. R to power 3, that must go from the set A to the set A. And let's see how things goes. So we follow the paths now. So okay, let's see what's happening. Now 1 goes to 1, and here 1 goes to 1, so we have that. 1 goes to 2, and 1 goes to 1, so we have 2 goes to 1. Now 3 goes to 1, and 1 goes to 1. 3 goes to 1, and 1 goes to 1, right? So we have 3 goes to 1, 4 goes to 2, and 2 goes to 1. So we will have 4 going to 1. This is r to power 3. Compute r to power 4. You will find out it to be r to power equals to r to power 3, and same thing for r to power 5 will equals r to power 3. And I will let you to confirm these things. And this brings us to the end of the section.